In this video we're going to look at examples of where a line will intersect a circle and an example of where a line will not intersect a circle. So here I have an equation of a line and an equation of a circle, and I'm wanting to find the points of intersection. Points of intersection will be where the x and y coordinates are the same in both equations. So what I'm looking to do here is to solve simultaneously. Now I can see the easiest way for me to do that is going to be to make the substitution, so to take the y value being as x minus 4 and to substitute that into the second equation. That would make the second equation x minus 3 all squared plus, here's my substitution, x minus 4 minus 1 squared is equal to 20. Expanding the brackets using my rule of square the first term, twice the product terms, so x times negative 3 is negative 3x, double that is going to be negative 6x plus 9 plus this becomes x minus 5 all squared. So again, square twice product square would give me x squared minus 10x plus 25 is equal to 20. Collecting like terms, that's 2x squared, what's going on here? Minus 6x minus 10 is going to give me minus 16x, and that's going to give me 34, so plus negative 20, that's going to be 14, which is equal to 0. I can see here everything can be divided by 2, so this is the same as saying x squared minus 8x plus 7 equals 0, and bingo, I can identify that that factorizes into x minus 1 and x minus 7, not 8. So my x values are going to be x equals 1 and x equals 7. Now I need to find the coordinate points, the coordinate pairs, so I need to find the associated y values. Well, to find y I just needed to do x subtract 4, so the associated y value here, x subtract 4 would be negative 3, and here x subtract 4 would be 3. So my coordinate pairs are going to be 1, negative 3, and 7, positive 3. In examples where we need to show that things do not intersect, we go about it initially in exactly the same way. We assume that they will intersect. So if they are going to intersect, then that's to say that x minus 2 squared plus, again, I'm making a substitution, so I'm taking the y value from here and substituting it here, so that would then be x plus 3 squared is equal to 10. So if these two things do intersect, this equation will give me a value for x. So I expand, so here I've got x squared minus 4x plus 4 plus x squared plus 6x plus 9 is equal to 10. Again, collecting like terms is going to give me 2x plus 2x squared, sorry, plus 2x is 13, and subtract the 10 is going to give me 3 is equal to 0. So if I can find an x value that solves this, then I'll have shown that they do intersect. But I've been told explicitly that they don't intersect. Now the fact that they don't intersect must mean that I can't solve that equation. And if I've got a quadratic equation that I can't solve, it must mean that the discriminant, b squared minus 4ac, is going to be less than 0. So the value of b is 2, the value of a is 2, the value of c is 3. b squared would be 4 minus 4 times 2 times 3 would give me 4 minus 24, which gives me negative 20, which is less than 0. So as the discriminant is less than 0, there are no real solutions for x. And as such, the lines cannot intersect. So there are our two examples. When we have intersection, we solve simultaneous equations. When we don't have intersection, we assume we can solve, and then show that we can't by using a discriminant argument.